Hi, so in this video, we're going to review guidelines for drawing a graph of a function. So this is on page 425 of your textbook, or otherwise in the section 4.6 at the end of limits at infinity and asymptotes. So we can see there's 6 steps here to determine everything we learned in algebra and then everything in so far in calculus. And we use technology as a support for our results, but they're not the answer to our results. We are the brain behind all this knowledge, right? So we're going to show that whatever we would get in technology, that we would get if we did it all but step by step. So it's really important that we do this. So we bring everything together, all the little pieces from algebra, from beginning algebra all the way up until now, bringing it all together into one package is going to be really important for us. So let's go ahead and begin. So the first problem we have is a polynomial of 4th degree. We do know a few things about polynomials. They're continuous, differentiable, they're smooth, and they have a domain of all real numbers. So we're going to go ahead and we know a little bit already. So right away, domain is going to be all real numbers, so negative infinity to infinity. So we got one down. The next part is to find the intercepts. So we do know how to find intercepts of polynomials. We know from pre-calculus and also chapter 1 that we can use the rational root theorem. So the rational root theorem states that, let me rewrite this, states that if we just take quotients of your last and leading coefficients and plug and chug until one makes a root, we can use synthetic division all the way down. So if I just take this polynomial here and rewrite it, I know that I can use the rational root theorem. So rational root theorem to take quotients of this last coefficient and first coefficient. We know it's a 1. We don't always write it, but we know it's there. So you just take all these combinations of 4. So plus and minus, plus minus. So in all its factors, right? All the factors. So usually a good rule of thumb with this, and I hope your algebra teachers told you this, was we always just use 1. We always start off with like 1 or -1, and then from there we start doing combinations. But we always start with 1 because it's always a good try. It's always a good guess. So if I just said, if I tried with x-intercepts first, because y-intercepts is pretty easy, right? I just plug in right away. Actually, the y-intercept is if I put in zeros all for x, and I'm just left with -4. So if I just started there, let's say where x is equal to 0, then we can see easily y is -4. So we do have a y-intercept at 0, -4. So at least we got that one out of the way. For the x-intercepts, now we can have to say that y is equal to 0. So using the rational root theorem, or RT, I'll start off with x equal 1, right? So if I would say, does 0 equal, right, the question mark, 1 to the 4th minus 2 times 1 cubed minus 3 times 1 squared plus 8 times 1 minus 4. And if I did this in the calculator, I would actually see that this is actually true, that 0 does equal 0, right? And we could just do it quickly in our head. 1 minus 2 is -1, -1 minus 3 is -4, and -4 plus 8 is +4, and 4 minus 4 is 0. So this does work out, and x equal 1 is in fact one of our roots. Because x equal 1 is one of our roots, we found an x-intercept. So right away, I mean, if I want to list it here, I can, comma, then I have a 1, 0, and see what else we get. So I'm going to go ahead and use synthetic division here. So I'll have 1, and then I'm going to draw a line and a little line here, and then put the coefficients of the polynomial. So it'll be 1, -2, -3, 8, and 4. And we always do like a dash here because we know that's the remainder of the polynomial of 1 degree lower. So I start here 1, 1, so drag it down. And of course, it's 1 times 1 goes here. And -2 plus 1 is -1. And then 1 times -1 is -1. And -3 plus -1 is -4. And -4 times 1 is -4. 8 plus -4 is +4. And then 4 times 1 is 4. And this 4 is a -4. So -4 plus 4 is 0. So that works out. So now we know what the lower degree is. So here now we know that 0 is equal to x minus 1, that first root, times, and then 1 degree lower. So x cubed minus x squared minus 4x plus 4. So at this point, we could keep going here one more time, but I do see now with the cubic, I see a nice grouping here. I can see that I can factor out an x squared and here a -4. So I'm going to get 0 equals x minus 1, and just watch what I'm going to do with 4 terms. I'm going to factor by grouping. So I'm going to have x squared here times x minus 1 minus 4 times x minus 1. And the reason why I did that, because I could see I was going to get this factor here. So just to check, x squared times x is x cubed, x squared minus x squared minus 1 is x squared, minus 4 times x minus 4x. And then this is the one where it's usually students get tricky. It's minus 4 times minus 1 gives you back the +4. And again, we want to take out the -4 so we can get a common factor. And this factors out really nicely. So now I have x minus 1 times another x minus 1 times x squared minus 4. So now we can see that we have some sort of multiplicity root where we have here, we're going to have x minus, well, I'll rewrite it. How about that? So you can see it better. So 0 equals x minus 1 squared times x squared minus 4. So this would imply, I'm not going to do all the work because that's for algebra classes, right? But we can see that x is equal to 1 and x is equal to plus or minus 2, right? Because 2 squared is 4, -2 squared is 4. So I'm sure you can see that as well. So we can say multiplicity 2, just in parentheses. So then we have the intercepts now, all of them, which are going to be, if I write them back up here, I'll have another 1, 0, and then here we'll have 2, 0, and -2, 0. And remember what this multiplicity 2 means. This multiplicity 2 means I assume that it's going to bounce off right here at 1. It's either going to bounce off upward or bounce off downward. Okay, so that's what the even multiplicity means. All right, the next thing that we're going to do that's listed here is finding local extrema and increasing, decreasing. Those kind of go together with that first derivative test. So let's go ahead and do that. I'll put number 1 here, right? This is like the zeros. The second step has to do all with the first derivative. So the first derivative we could say is y prime is equal to, and then we could just take the first derivative. We can easily see that's power rule all throughout. So a 4x cubed minus a 6x squared minus a 6x plus 8. And I'm just looking directly right here. Derivative of x to the fourth is 4x cubed. Derivative of minus 2x cubed is 6x squared. here 6 minus 6x, and then plus 8. And then, of course, this just annihilates to 0. So with this piece, I do see that there's a common factor here of 2. So I'm going to go ahead and factor out a 2. And again, what we want to find are critical numbers. Once we find the critical numbers, we determine which ones are local extrema. Because this is a polynomial, we won't have anything undefined. So we know that these critical numbers represent something just for the fact that it's a polynomial function. So if we go ahead and set this equal to 0, I'll factor out a 2. So we get 2x cubed minus 3x squared minus 3x plus 4. And that way, at this point, we can go ahead and try to factor. Once again, we can use the rational root theorem. If I divide each side by 2, this kind of goes away, right? So we get 0 equals. And if I just go ahead and take, again, the rational root theorem, right? Quotients of 4 and 2, that's going to be 4 divided by 2. So I'll do it over here, rational root theorem. It's going to be plus or minus, and then 2. So any combinations and its factors, right? That's the rational root theorem. But what do we always pick? We always pick 1, right? Like that's the main one we always choose, and then we kind of go off from there. So if I put in 1 here, right, I do see I get 2 times 1 is 1, minus 3 is negative 2, negative 2, 2 minus negative 3 is negative 1, and negative 1 minus 3 is negative 4, and 4 plus 4 is 0. So 1 is actually a root. So we did find that root by using, and then I'll put right here. So always try 1 first. And usually it's plus or minus, the positive or negative one usually works. So at that point, we just need to find the rest of the factors, right? So we can go ahead and do a quick synthetic division once again. Okay, so let me do that right here. So I'll have a 1, just like I did before, little bar. And I'm just going to move this down here so I have a little more room. There we go. And I'm going to put the coefficients 2, negative 3, 4, dash the line, and there we go. And then begin synthetic division. So once again, I just dropped the 2 down. 2 times 1 is 2. Negative 3 plus 2 is negative 1. Negative 1 times 1 is negative 1. Negative 3 plus negative 1 is negative 4. Negative 4 times 1 is negative 4. And 4 plus negative 4 is 0. So that means up here, that will leave us with a 2x squared minus x minus 4. So when I do this, it's not so obvious. And again, this work is going to take longer as you go deeper into math. That's why I notice I have 3 problems, because 3 problems can essentially take the 1 to 2 hours of work, right? But it can go fast if you recall your algebra as good as you possibly can. That's why it's really important that we review chapter 1 and you really have a good foundation. You know, when your algebra teacher said, you're going to need this, you're going to need this, now you can feel that you really did need it, right? So I always say rational root theorem when you need a factor, always try 1 or negative 1 first, and then synthetic division. I really do like synthetic division more than long division because it's a little quicker. But other than that, we can see that we have 2 roots. We have x equal 1, once again, as a critical number, right? So maybe we can put C here for a critical number. And then here, notice that for this factor, I can't factor. There's no 2 numbers of negative 8 that will add up to be negative 1. So I do know that to find the critical number here, so 2c squared minus c minus 4 equal to 0. I'm going to have to do probably a quadratic formula, complete the square, however you want to do it, whatever's quickest for you. So we can just do quadratic formula. So let me draw like a little line. And then here we could just say, well, C is equal to, right, negative B, so negative, negative 1 plus or minus the square root of, B squared, so negative 1 squared minus 4 times A times C. All over 2 times A, so 2 times 2. So we just can see here that this is going to be positive 1 plus or minus square root of 1 minus a 4 times 2 times negative 4. So that's going to be 1 plus 32. So 1 plus or minus square root of 1 plus 32 is 33 all over 4. So there are your critical numbers, and it's plus or minus. So if you wanted to approximate just to get an idea on a number line, that's you can just put that in the calculator, but it's a little less than 1 and a little less than 0, negative, and then a little above 1. Oops. Okay, so at least we have the critical numbers. I'm going to star this. Okay, so what we're trying to do, let's remind ourselves, we already did the first part, the algebra part. Now what we're trying to do is find local extrema and the increasing decreasing, which is that first derivative test. So now what we can do is just go ahead and put these on a number line. So if I just put these on a number line here, where I would have the two critical numbers of 1 minus square root of 33 over 4 and 1 plus the square root of 33 over 4. Now, what you could do again is put it in the calculator and get decimal approximations, and then you can determine your test values. I'm going to go ahead and choose, I know one is negative and one is positive, so I'm just going to choose, oh, and then 1, I need to put 1 on there, sorry. 1 is in the middle. There we go. Circle them. So we know these are our critical numbers. And then we'll put y prime up here, the sign of y prime, and then the function itself. What does that mean? So I do know that this one is negative and this is 1. So I'm going to put 0 here because I think that's a good one. And then I'll put, this is a little less than 1, so negative 2. And then in between 1 and 1 plus square root of 33 and 4, I'll put 1.5. And then over here, we can choose anything we want above that. So 5 or something like that. Put 2. Okay. All right, so when I put it into the derivative, these test values, I do see that if I put it in, let's say here, because this is the derivative but just factored, I would get negative 2, negative 1, that's a negative. And then here is positive, minus, minus. So it would be negative times negative, which is, positive times negative, which is negative. So this one's going to be negative, and then you can go ahead and put in 0 here to the derivative. We get a positive number 8. Right. And then I can see the pattern. Polynomials have that wave, right? That pattern, which means for the original function, it's going to be decreasing, increasing, decreasing, increasing. And then we see that there's going to be a local min here, a local max here, and a local min here. Okay, so I think we have all the pieces that we need. So the first thing I'll go ahead and fill in is the increasing, decreasing. So it'll be decreasing, or let's see what's first. Yeah, increasing on between 1 minus the square root of 33 over 4 up until the next critical number, right? It's increasing here from here to 1. union, and then it's going to jump over to that other root out to infinity, right? So 1 plus square root of 33 over 4 out to positive infinity. And again, I'm not using a calculator. I'm just estimating. The only thing I wanted to check maybe in a calculator are approximation values for that to choose my test values. Okay, and then it's decreasing everywhere else. That means it would be decreasing on negative infinity up into that one root or that one critical number. Union, and then decreasing again from 1 to that other critical number, or in plus square root of 33 over 4, like that. And that would imply that our local maxima is going to be at these values. Now, you could put them in as points. Yeah. So we know there's local maxima, and then once again, you can put in the points if you like. It's not necessary, but we can. And we know there's one local max, that's the easy one at the 0, right? At 0, 1. At 1, 0, I'm sorry. So 1, 0 is the max. And then there's local minima at those other critical numbers. So the first one is at 1 minus square root of 33 over 4, right? If I scroll here, those are where the two minimum are, right here. So we have 1 minus, and then if you just plug and chug that in, you're going to get like a y value of around negative 12.39. And then the other minima is at the other side, which is 1 plus the square root of 33 over 4. And that is pretty small y value at negative 0.54. So I went ahead and just I just plugged and chugged these to get into the y right here, the original y, just to get the ordered pairs. So it's really up to you. You can put it in the calculator on that table and plug and chug values. It's up to you. The last part is this whole thing, points of inflection. Of course, we can see we're going to have a point of inflection definitely in between these two, right? It's going to go concave up and then it goes down and up. So we're going to have 1, 2 right there. I can see it already. So here, so now let me go point number 3. Now we're going to set a first derivative. We're going to talk about the second derivative. And you can kind of see now the method, right? All the processes. I start with the algebra, then I talk about first derivative, then I talk about the second derivative. So let's go ahead and take that second derivative, which is going to be 12x cubed minus 12x minus 6. Okay, and if I go ahead and set that equal to 0, and I'm going to reduce by a factor of 6 at the same time. So I'm going to have 2x cubed minus 2x minus 1. All right, and if I go ahead and do that, did that wrong, 12x squared. Sorry about that. Cubed. I can see that this is easily a quadratic, and I can use the quadratic formula once again to solve for the critical numbers. So let's go ahead and do that. So I'm going to get 2c squared minus 2c minus 1. And so I'm going to have c is going to be equal to negative b, negative 2, plus or minus the b squared, negative 2 squared, minus 4 times a times c, all over 2a. So I'm going to have 2 plus or minus, and then here I'm going to have 4, and then the minus is a plus, so 4 times 2 is 8. So 8 plus 4 is 12. So this the square root of 12 all over 4. Now I'm going to go ahead and reduce this a little bit so we can get c equal to 2 plus or minus 2 square root 3. Just reduce out that 12 with 4 times 3, right? And then square root of 4 is 2. And that way, when you get the 4 on the denominator, you can go ahead and reduce out a 2 everywhere. So if you reduce out a 2 everywhere, you get a 1 here, 1 coefficient, and a 2 at the bottom. So you'll get 1 plus or minus square root 3 over 2 equals to C. Now, in order to determine concavity, we do have to do that number line. So when you do that number line, you're going to have 1 minus square root 3 over 2, and then 1 plus square root 3 over 2. And I can tell that this is going to be negative from 1 minus that, and then 1 plus will be positive. So if I go ahead and just draw my little line here, do this kind of quickly since we kind of get the hang of it now. We're going to have y double prime here and then y prime here. So I'm so sorry, just y there. Okay, so here I can pick 0 and then maybe -1 here and positive 2 here. So if I put -1 into the second derivative here, I can see that I'm going to get 12 plus 12 minus 6, so that's positive. 0 will be negative, and I can see the pattern. That means that for my original function, it will be concave up, concave down, concave up. So I can see the points of inflection and then my concavity intervals. So now let's go ahead and go back and write that in. So now we have points of inflection at those critical numbers of the first derivative, which is 1 minus square root 3 over 2. And if I plug and chug that into y, if I put this into every x in y, I end up getting something like, and I did this at -7.2. Okay, and then the next one will be 1 plus the square root of 3 over 2, and I just plugged and chugged that in for points, again, maybe using the table on my calculator, -2.9, and then concave up on those intervals and down. So it looks like we're only concave down in between, and then everywhere else is concave up. So -infinity, and then 1 minus square root of 3 over 2, union 1 plus the square root of 3 over 2 out to positive infinity, and then concave down in between those critical numbers of the first derivative. So you can see all the work that I did to graph, and then all that's left is really to graph it here using everything on this. So we have here, let's go ahead and graph the intercepts at 0, -4, right? 1, 0 is a bouncing multiplicity 2, 0, and then 2, 0, and -2, 0. We know we have a local maximum at this 1, 0. So we know at 1, 0, it's going to look like a maximum, right? And then, and local minimum would be at these values here, these points. So let me go ahead and draw it. See, negative, like 2, right here. Oops, sorry, there. And then it kind of curves. And then it goes, it's kind of weird. It kind of goes like here, really close. So like, let me erase this. All right. And then all the way up. And this is going to be the tricky one, this 0. So it kind of goes like, and then just kind of curving there. I'm going to redo this piece because it's kind of hard when you're left-handed. There we go. So there you go. And then you can go ahead and label all the points. I encourage you to. I use Desmos. I use Notability, so I can do 0, -4, putting little dots there, like that. Oh, that looks too big, but You can always do like a nice size here. And then there's some critical values all in between, like here's a change, the concavity change. Right here is the point of inflection, right? So there's all these other points that we can put in from here with local minima, points of inflection. So here are all our points right here. Points, intervals, right? So that's the process of a polynomial of any degree using sketching the curve by the process of the graphing in the calculus class.